My name is Huang. People usually call me Amy. I graduated from University of Wisconsin-Madison. I also spent a year visiting in UCSD. My advisor is Stephen Sam. I'm currently working as a postdoc in Texas A&M University. I'm working with Professor J.M. Lansford. So my research focused on using the tools from representation theory, commutative algebra, and algebraic geometry to solve a variety of problems. I'm interested in finding minimal free resolutions and equations of varieties that are invariant under group action, especially if your varieties can be parameterized or desingularized by vector bundle on a homogeneous variety like flat varieties or Grassmannians. In this case, there is a powerful tool, which is called Kempf-Weyman geometric techniques, that when your varieties are good enough means that if your varieties are normal and with rational singularities, then these tools can give you the full minimal free resolution of your variety. However, if your varieties are not so good, if your varieties is not normal, then the usage of these tools are very limited. And I'm developing ways of extending these tools to deal with those non-normal varieties. I also work on finding equations of nilpotent orbit closures in type A. So if you look at fix a single nilpotent matrix, look at its conjugacy class, and then you take the Zariski closure of the conjugacy class. This is what's called nilpotent orbit closures in type A. In 1989, Weyman worked out the defining equations for those nilpotent orbit closures in characteristic 0. And recently, I worked out those minimal defining equations in characteristic 0. And I'm also developing tools to extend those results in characteristic P. I'm also interested in finding and using unexpected symmetries in CCGs. So let me introduce one of the projects in this direction that I worked on. So if you look at X, which is just space of n by n matrices, so there is a natural group acting on it, which is GLM cross GLN. This will act on your matrix via row and column operations. So it will induce the corresponding action on the coordinate ring of X, which now we think of it as just the symmetric algebra. So since so we're interested in those ideals that are invariant under this GL action in your coordinate ring. So since GL acts on your ideals, so it will induce an action on the CCG module of your ideal. So a natural question to ask is, how do we describe this CCG module as the GL representations? And basically, I answered this question using an unexpected symmetry in the CCG module. So we know that the action of GL acting on the CCG module, it will induce the action of the corresponding Lie algebra. However, there's another algebra acting on your CCG module, because if you take the dual of your torsion module, this is your X module. So the X group would act naturally on your CCG module. And in this case, the X group of the trivial module is just the exterior algebra. So we have two algebra acting on our CCG module. And in fact, you can combine this action of these two algebra to make it a module over a much larger algebra, which is the general linearly superalgebra, GLMN. And this GLMN is in fact a Z mod 2Z graded Lie algebra. And in fact, you can lift the Z mod 2Z grading into a Z grading. And if you look at the degree 0 piece, this is exactly the Lie algebra of the GL group. And the degree -1 piece will encode the algebra of the X group. And together, this will make your CCG module a representation over this GLMN, and I use this to write down explicit combinatorial formula for all those CCG modules as GLMN representations. I also worked with applied mathematician Jiafang Lu in concerning a numerical method in studying quantum maniability systems, and this numerical method is very broadly used, which is called quantum Monte Carlo method, and we explore the limitations of this numerical method. In the actual talk, I'm going to focus on my projects about tensor ranks and matrix multiplication complexity. In the first half of my actual talk, I'm going to discuss how do we relate the difference between three notions of tensor ranks to a very well-studied subject, which is called polynomials with vanishing Hessian. In the second half of my actual talk, I'm going to discuss how do we explicitly compute the border rank of a very specific tensor 3x3 permanent, and how does it relate it to the study of matrix multiplication complexity. So I hope you will enjoy my actual talk, and thank you.